네, 안녕하세요. 저는 소개해 주신 것처럼 카이스트 산업 및 시스템 공학과의 이다빈이라고 합니다. 근데 여기 혹시 네, is there a non-Korean speaker? I saw one person who's non-Korean. Okay. But I'll go in English anyways. Okay, from now on. Um, well, I was asked to speak in English, so okay. I saw also two high school students in the audience. Could you raise your hand, please? Okay. Wow. Um, uh, it could be a little bit difficult for you guys. I guess maybe. Okay. Are there undergraduate students? Could you raise your hands, please? Okay. Have you guys taken undergrad optimization courses? No? Linear programming? Uh, Graph theory, okay. Anyone has not taken optimization, like linear programming? Okay, not many. Okay. It's not too difficult to follow the linear programming part. I try to make these lectures, self-contained. But if you have some materials that are, you guys are not familiar with, I can suggest some reference materials later. Okay. But if you have kind of questions or problems following the lectures, please let me know, then I can give you advice. Okay, good. I got into this area when I was a junior student in undergrad. I got interested in like optimization and algorithms in general, but when I was a student here, I was not able to find many courses about optimization and algorithms. So I ended up visiting some university in Canada, and that department was offering many topics and courses on this kind of stuff like algorithms, graph theory, and algorithms, and that was really fascinating, and that was the motivating point for me to study these topics for my PhD studies. And I'm really glad today that I can cover these lectures in Korea so that you guys can get exposed to this topic. I'm taking care of optimization courses at KAIST, but this is sometimes cover some technical level topics like this at KAIST because maybe not many students are not that interested in this kind of stuff. So it's a good opportunity to introduce all this fascinating stuff that I learned like 10 years ago. And I hope that you guys also enjoyed it. Okay. As announced, I'm managing my website to upload these lecture materials. So I'm trying to prepare lecture notes before each lecture. So let's say I have uploaded lecture notes up to lecture 5. So it should cover, and I'll soon upload lecture notes for 6th lecture. So it will cover lectures up to Wednesday. So if you have time tonight or tomorrow, just if you are interested, just go to the website and just look into what will be covered there, and it'll be useful for you to follow the materials. Okay. And also, it could be quite technical. That was my feeling 10 years ago. So I try to write down every detail as possible in the note. I'm making lecture notes as easy as possible. But still, if you have problem, going through or digesting some steps, just please let me know, and you can also always ask questions offline and email me, and so forth. Any questions about the logistics about this lecture series? Okay. Right. Okay. Okay. So let's introduce what this course is about. So So I was studying like the history of combinatorial optimization when I was preparing for these lecture materials. So the first development about this topic dates back to 1784 when this guy Monge studied this something called the assignment problem. And the background for studying this assignment problem is something about Earth moving problem. So you have Earth of dust, and you are trying to move this to some different locations. And like, what would be the best way to move this kind of big, chunk of dust into some different location? And this is relevant to something called optimal transport. And this is a kind of important problem in probability theory. And the idea is that, if you look at the probability distribution, it can be viewed as the chunk of dust and you are moving it to some different area. Okay. And then I think the big achievements and the progress has been made in early 20th century. And I think the two problems are the important contributions. So the first one is bipartite matching. So we're gonna get to this later. And also linear programming. Okay. So people have studied or used linear programming like many years ago, but then people, including George B. Danzig, developed efficient algorithm for solving complex linear programming problems. Okay. I think even high school students might have learned some kind of easy linear programming problems. Like you have some constraints, you have some like materials that are available to you, and then you want to produce some items and goods out of these materials so as to maximize your profit. Okay. Okay. But later on, with the advent of efficient computers, we are facing big contributions and achievements and progress in many different domains, like semiconductor chip design, and even new drug development, manufacturing, and online platforms. Okay. All these places I have applications from combinatorial optimization. Okay. So I think this is exciting area. Okay. So motivated by these many applications and also elegant history about things, the course aims to teach you, some in-depth understanding about combinatorial optimization. I'm given only 12 lectures. I think when I was a PhD student, I took like at least 3 or 4 courses just on this topic. So there is a vast area, and then if you look into the textbooks I listed in my syllabus, if you click on one of them, you can find like this thick book just written on combinatorial optimization. So it's a deep area. But I was thinking about what to cover and what would be the best way to deliver kind of good ideas and important things about this topic. So I have decided to focus on a few problems, like 2 or 3, and then I'll just cover kind of things in depth. Okay. I'll try to give you as many ideas as possible from a small number of topics, okay, which I think are most important in modern area of algorithms. Okay. That's the main objective. The first half, we'll just focus on something called the matching problem. Okay. Anyone who have heard of this matching problem? Could you raise your hand, please? About half of you guys. Okay. So the matching problem is easy in the sense that we have a polynomial time algorithm. But the algorithm design itself is quite complicated. Like understanding how it works, maybe the algorithm is easy, but understanding how it works and analyzing the time complexity can be difficult. So I'll just go through every detail of the analysis and the kind of intuitions behind them, and that will be useful to you. And in fact, there are, different algorithms from different angles. So like purely combinatorial algorithms that walking through like graph theoretic concepts, kind of enumerating vertices and edges, and so forth. But there's a completely different style of algorithm, which is based on linear programming. And the linear programming based methods is kind of continuous, and that gives you another perspective about how to solve this. And I think graph theoretic approach and linear programming based approach are the two backbones for this area. And if you kind of stick to the first half of this course, you'll understand what I mean by that. Okay. And then I'll move on to something more recent, which is about submodular function optimization. And we have submodular minimization and submodular maximization. So I guess if you guys have, so submodular function is a non-linear function class. You guys already know that maybe convex minimization. So we know that convex minimization can be solved in polynomial time. But in contrast, convex maximization is a difficult problem. Submodular minimization is easy, and submodular maximization is difficult. But both of the problems have important applications in many areas. So I'll cover these two topics as well. They will give you some different flavors and ideas about them. And I'm a bit more ambitious, so I try to briefly touch upon the last topic, which I found quite important in practice. I'm not like a heavy industry project guy, but I worked with Samsung Electronics about their semiconductor design problem, and in that problem, typically the problem setting is not given to you, so you have to learn and estimate what's going on behind the scene, and then using that estimated parameters, you need to make a right decision. And I learned that this area of black box optimization is quite useful for that. So I'll just briefly touch upon that. And if you get to work on industry and you're maybe like in practice, the last topic might be the most relevant thing to you. Okay. But this is kind of ambitious, I guess, list of topics. I might run. I might not have kind of enough time to cover all of the things, but let's see. Any questions? Okay. Yeah, I'm a bit nervous. I don't know why, but so if you have any kind of questions, that would be great. So this is my first time teaching this material. So I guess I spent like the last few weeks about developing these materials. I might have many typos in the notes. So if you have found any, just let me know. That will be very useful. Okay. All right. So let's get started. So lecture 1 is about introduction to bipartite matching. Okay. So again, as I said, the first half will be about the matching problem. And the matching problem itself has two parts: bipartite matching and non-bipartite matching. But you can believe me that non-bipartite matching is quite complicated, but it's a simple variant of the bipartite matching problem. Okay, I'll explain that throughout the course. All right, so today let's start a bit easy. So we're gonna go through basic materials for graph theory, and then I'm gonna introduce the bipartite matching problem. And lecture 1, I will explain a simple algorithm, which is a greedy algorithm, but that is not giving you an optimal matching, but it will give you a nice approximation algorithm for the matching problem. Okay, and I will explain that. All right. So So this is a famous problem in graph theory. So if you start reading a textbook on graph theory, you'll run into this scenario. So this is the medieval city of Königsberg, and I think it's now part of Russia, I think. And this picture shows you kind of city map of this old city. Okay, and if you look at that, there are some islands in the middle, and there's a river going around them. Okay, so this is one island, and there's another island here, and there's this north and south part. Okay, and the red things, they are the bridges connecting the north and south to the island. Okay. I did my PhD at a school called Carnegie Mellon University, and it's located in the city of Pittsburgh in the US, and that has the same kind of landscape of the city. Though. Anyways, so there are many bridges connecting different regions of the city, and the question is the following. So I want to start from, let's say, the north. Okay, so my house is located in the north. And my question is, I want to somehow kind of travel in this city by doing the following thing. So I want to cross or traverse each bridge exactly once, not twice or third times, or not zero. I want to use the bridge just once. If I cross a bridge, I don't want to come back. Okay, so you traverse each edge exactly once. Okay, and then I want to go back to the same location. Is it possible? Let me give you maybe 1 minute to think about the answer. Okay. Maybe like many of you have already know the answer. But let me give you 1 minute to think about, or even like how to argue this. How to argue that the answer is no. Okay. Well, I guess like if you start kind of drawing paths connecting different regions using the bridges, you'll kind of realize that, that's not possible. But to formally argue that the answer is no, it's useful to draw something called a graph. Okay, so a graph is an abstraction of some objects, just focusing on connections. Okay, so we have 4 different regions, right? So each region can be represented by something called a vertex. I'll get back to this later. So I have 4 different regions. I have 4 different vertices: green, yellow, orange, and purple. And the bridge is basically connecting 2 different regions. And in the graph, I'm connecting the 2 vertices that are representing these 2 different regions. Okay, so let's say I have 2 bridges, B1 and B2, connecting the yellow and green regions. I am drawing connections between these 2 vertices. And these are called edges. Okay. So once you draw the figure on the right, just it's easy to argue why coming back to the same location using each edge exactly once is not possible. The reason is that the reason is the following. So you start with, let's say, the vertex G. Okay. Now you need to leave this region and you go to a neighboring region using a bridge. Okay. And then you are leaving this region and somehow take some path, and then you go back to this region, G again. Now what you realize is that when you enter into some region, let's say Y here, when you leave the region, so you eventually need to leave other regions, and you go back to the same vertex G. What you realize is that when you enter into some region and leaves it, you are consuming enter and leaves consumes even numbers of edges or bridges. Okay, so let's look at this graph again. Let's say you are enters into Y. When you leave, you're using 2 bridges. And later, maybe you are also enters Y again. But you need to somehow leave the city. Otherwise, you cannot go back to the same location, G. So you need to leave this Y again. But again, you're using 2 bridges. Okay. But if you look at this graph, every vertex has odd number of edges connected to it. So the question is, the answer to the question is no. Okay, using this simple idea. So graph theory, or this concept of graphs, enables you to, I can argue about these networks and connections in a simple manner. Okay, and that's what we're gonna learn today. So there are several elements for graphs. So a graph consists of vertices, or you enumerate each one vertex, the second vertex, and so forth, and the plural is vertices. And you have a set of edges. Like this, you have the vertex set phi is given by green, yellow, orange, and purple. And the edges set is given by the 7 bridges. Okay. So whenever you are given a graph, it consists of the vertex set and the edges set. Okay. And 2 distinct vertices, let's say U and V, are called adjacent if there's an edge between them. And here, G and Y are adjacent because there's an edge connecting them. But whereas G and orange, they are not adjacent because there's no edge connecting these 2 locations. Okay. Just remember this terminology, adjacent. And so when 2 vertices are, let's say, okay. So G is adjacent to Y and it's adjacent to purple. In this situation, we call Y and P neighbors of G. Okay. So if vertex V is adjacent to vertex U, then we call V a neighbor of U. Okay. It's good to know this terminology again. The next terminology is that when you have a vertex U and it's connected to some edge E, then in this case, we say that this edge E is incident to vertex U, or the other way, this vertex U is incident to edge E. These are just common terminologies in graph theory. Okay, it's good to know them before we start the main materials. All right, and okay, and the last terminology is the following. So if you look at let's say vertex U here, and let's say you have 3 neighbors like X, Y, and G. In this case, we say that the degree of U equals 3. It's just it just counts the number of neighbors of this vertex. Okay. Okay. The next thing. Okay, it has to be repeated. Okay. So now I'm gonna give you some examples of graphs. The first class of graphs is called complete graphs. So how is it defined? So I have a set of vertices, let's say 4. What I do is I add an edge between every pair of 2 vertices. So I have, let's say U, V, W, X. Then I have an edge between U and V, U and W, U and X, and also VW, Vx, and Wx. So I have 6 pairs of 2 vertices, and I'm adding an edge between every pair of it. Okay. And also, you can also draw 3 vertices, and you have 3 pairs, and adding all edges to them. You can also do the, let me do the case of 5 vertices. I have 10 edges because there are 10 pairs. Okay, these are 10 pairs. So G, a graph G VE is complete if there's an edge between every pair of 2 distinct vertices. Okay. The second class of examples are bipartite graphs. Okay. Bi typically means 2, and partite means you are partitioning some set into different numbers of sets, but we are partitioning the set into 2, and that's why we are calling them bipartite. Okay, so how do we do this? So let me give you an example. So you have one set of vertices, let's say 3, on the left, and I have another set of vertices on the right, 2. Okay, and I can add an edge between one vertex from the left and another vertex from the right. You cannot take 2 vertices from the same side. You always need to take on a vertex from one set, and the other vertex has to be coming from the other set, like this. Okay, so this is called a bipartite graph. Or for example, I can add more or 2. This is bipartite as well. Okay, graph G is bipartite if the vertex set V is partitioned into 2 V1 union V2 such that every edge has one end in V1 and one end and the other end in V2. Okay. So as soon as you are adding an edge between, let's say, these 2 vertices, you are destroying this bipartition structure, and the graph is no longer bipartite. So this is not possible for bipartite graphs. Right? So far we have talked about 2 classes of graphs, complete and bipartite, and in fact we can combine these 2 concepts. So the next one is complete bipartite graphs. That is, so you are again, so this has to be bipartite, okay? But let's say 3 and 2. What you do is you are taking every possible pair of 2 vertices where one from one is from one side and the other one is from the other side. So you take every pair of two vertices from one left and right, you're adding all possible edges. And this is called complete bipartite. Let me add one more vertex. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay. So bipartite graph G is complete if there is an edge between U and V for all U from one side and V from the other side. You don't have to worry about kind of writing down everything written here. We have lecture notes. I just kind of write things down just to explain things. Okay. But if you have a problem understanding my writing, just let me know. Okay. Students have always complaints about my writing. Anyways, okay. Any questions so far? Okay. Great. So far was the most basic concepts about graph theory, and let me move on to something more relevant to this course. Okay. Let's start with the concepts of path. Okay. There are like different ways of calling different concepts, but let me stick to the terminologies due to Doc West. I guess some students have taken graph theory course already. Doc West's book is one popular textbook for graph theory materials. So I'll stick to the terminologies there. But just, I guess, you might kind of stumble upon different styles of terminologies, but it's good to understand what I'm referring to. Okay. So the first one is a walk. Okay. So a walk is just a sequence of vertices. That's it. Okay. But when you move from one vertex to the next vertex, you need to use an edge. You cannot just jump from one vertex to a non-neighbor of it. When you move from one vertex, you need to move. You can move to its neighbor. Okay. So, in other words, so V0, V1, there's an edge between them, and also there's an edge between V1 and V2. So every two consecutive vertices have to be adjacent. That is the restriction. So if you look at this example on the left, so what I do is I start from the leftmost one, V0, and I move to V1. Again, you use an edge. You can move to a neighbor, not to a non-neighbor. And then you move to the second one, V2, and V3. And I can go back to one of the vertices that I have already visited. Okay, so V1 and V4 are the same ones. And then from V1, I go to the rightmost one, which is V5. This is a walk. Then what is a path? So okay, on UV walk, it's just that if you just specify the first vertex and the last vertex, then it's called a UV walk. It just means that you start from U and it ends with V. Okay. And a path is that it's a walk, but you cannot repeat vertices. That's just a path. So if you look at the second figure here, you just go from V0 and you move to the neighbor V1, V2, V3, V4. But the left one is not a path because you're repeating this V1 and V4. Okay. And again, on UV path. So if you specify start vertex and the last vertex, then you have a UV path. Okay. Okay, the next related concept is our cycles. Okay. So we have a walk. Okay, it's just a sequence of consecutive vertices. What is a closed walk? You are imposing one more condition to a walk. That is, the first vertex, the starting vertex, and the last vertex have to coincide. So when you start from one vertex, you have to go back to the same vertex. That's a closed walk. So if I just draw an example, you start from V0, and then you do some traveling, but eventually you are going back to the same vertex. So these vertices are repeated. Closed walk has to go back to the same vertex. A cycle is similar to the concept of path in the sense that a cycle doesn't allow repetitions. Okay? It's a closed walk, but no vertex inside is repeated, except for the first one. Okay, so that's the cycle. So let's look at some examples. So here you start from the top vertex V0. You go to V1, V2, V3, 4, 5, 6. So you go back to the third vertex again, and V7 and 8. So it's a closed walk because it's a walk. You have a sequence of vertices using edges, and you are going back to the initial vertex V0 at the end. But this is not a cycle because V3 and V6 are the same. Okay. But the second example is a cycle. So you start from the top vertex and you just go to neighbors in the clockwise fashion, and you go back to the top vertex again. So this is called a cycle. Just to note, I guess for those of you who have taken graph theory courses, for matroids, these are called cycles, and these are called circuits. But you forget about this one. But don't get, I guess, for those of you who are familiar with matroid, don't get confused with, I guess, cycle circuit and stuff. We focus on cycles that are not repeating vertices. Right? Any questions? Okay. The next concept is about lengths of paths and cycles, and also parity. So the length of a walk, just count the number of edges you are using. And now that you have defined the notion of length, you can compute the length of a path. So you can have many paths between two pairs of vertices, between a pair of two vertices. Now you can collect a path that has the minimum length, and that's called the shortest path. For example, you have these two vertices U and V, and let's say I have a path of length 2, and I have a path of length 3. The shortest path is the top one. Okay. The bottom one has length 3, whereas the top one has length 2. Another related concept is this odd cycle. It's just that it's a cycle whose length is odd. There are an odd number of edges on a cycle, then you call it an odd cycle. Okay. An even cycle then has an even number of edges, then you have an even cycle. And for example, you have a triangle. This is an odd cycle. But if you have this rectangle, it's an even cycle. Okay. I guess the last graph theory concept, okay, which are quite also straightforward. So let me explain this concept of subgraphs. Okay. So you have a graph G. Okay. I guess a subgraph is that you are just taking a subset of vertices and subset of edges. That's it. That's the notion of subgraphs. For example, we have this closed walk. If you take, I guess I took just 5 edges, and the vertices that are spanned by these 5 edges, this is a subgraph. And also the second one, collecting only 4 edges from the original graph, it's another subgraph. So when you take a subgraph, there's a restriction. There's no restriction about taking which subset of edges you are taking. But there's another concept related, which is on induced subgraph. Okay. So it's a kind of a subgraphs, but the way the way it is picked is different from that. So there are more restrictions about the way it is picked. So what you do is you take a vertex subset first. Okay. Let's say you are taking V2, V6, and V5 and V4. And then you are adding all edges between these vertices. So there's an edge between V2 and V4, then you include that. Okay. If there's an edge between V4 and V6, you have them. And V5, V6, V4, V5, you include them. Then you get an induced subgraph. But if you look at the second graph, this is not on. Oh, this is also an induced subgraph, I think. Okay, and this is also an induced subgraph, right? Oh, no. Okay, well, let's assume that you are having an edge between V2 and V1. Okay. Well, let's say you are taking this vertex subset of V1, V2, V3, V4, 5, 6. Then the induced subgraph has to include the edge between V1 and V2. But if you don't have one, then the second graph is no longer an induced subgraph. Okay. Any question? 아, 예. 아, 네네네.
그 인듀스 서브그래프 정의에서 그 말씀해주신 대로 인듀스 서브그래프의 그 어드제인슨시가 오리지널 그래프의 그 어드제인슨시를 따라가야 되는데 이 정의를 보면은 이게 그냥 항상 컴플리트 그래프가 돼야 되는.
제가 is there a mistake in the definition? Is a subgraph of G defining vertices so that UV is an edge if and only if and okay. Has to be a mistake, and UV is an edge. Great. There should be many typos and mistakes, so it's always it's good that you are following the lecture. Thanks. Okay. Any other question? Yes, these are quite easy. All right. And in this case, I mean, it's just equivalent terminology, but when you have a graph, induced subgraph, you say that this is a subgraph induced by this vertex subset U. Okay, so every time you have a induced subgraph, it's associated with a vertex subset. Okay, so when you want to specify this vertex subset from which you take an induced subgraph, you write or use this expression. And the last one is there's this notion of cliques. Okay, clique is just people just always confused with, I guess, complete graphs and cliques. It's just that this is a subgraph that is a complete graph. So I guess even in the kind of in the literal sense, when you have a community of people and friends, we say, oh, there's a clique of 3 people, and in that sense, we are using this terminology of cliques as a subgraph. When you have a complete graph in a subgraph, you call it a clique. Okay, so we are done with basic graph theory. Let's now we are ready to kind of get into this bipartite matching problem. So we have defined this notion of bipartite graphs. Again, a graph is bipartite if you can partition the vertex set into 2, and an edge has to cross these 2 sides. Okay. Well, there's an equivalent definition of bipartite graphs. Okay. The first one, okay, so we need this result here. So if you have a closed walk that has an odd length, okay, it could repeat vertices. Okay, but you can always find an odd cycle contained in it. What it means is you can repeat vertices when you define a closed walk, but you can get away from this vertices repeated. For example, if you take, you start from this vertex, instead of going into this loop, you just directly avoid it. And if you go back here, this is on path. This is a cycle. It's not repeating any vertex. You can prove that on any closed walk of an odd length has to contain an odd cycle. But maybe writing down the proof can be a bit difficult. So I leave it as an exercise to prove this tonight. Okay. Just use the definitions of walks and cycles and paths. Just try to write down your own argument. Now, if you use this thing, what we can prove is the following characterization of bipartite graphs. The graph is bipartite if and only if it doesn't have an odd cycle as a subgraph. Okay. Let's prove this. But given that we don't have much time for lecture 1, let me write down the important proof ideas for you. Okay, and then the proof and in detail can be found in like the lecture note. So let's prove this direction. Okay. Suppose that G contains an odd cycle C. Okay. Let me draw a cycle of length 7. Okay, I have V1, 2, V2, V3, 4, 5, 6, and 7. Okay. And let me partition my vertex set into 2, left and right. And I'm going to assign each vertex to left or right. Okay. Let's include V1 as left. Let me use a different color. So V1 belongs to the left side. You know what? Using this definition of bipartite graphs, 2 vertices that are adjacent have to belong to different sides. Right? So V2 has to go to blue, right? So let's say, let me give you V1. This is V1. And V2 has to be in the second side. So V3 is a neighbor of V2, so it has to be red. And V4 has to be blue. And V5 has to be red. V6 has to be blue. V7 has to be red. Now you run into a conflict because the cycle is odd. Okay. So when you have an odd cycle, it cannot be bipartite. So this is the main idea. Let's look at the other direction. Suppose that G has no odd cycle. And I want to prove that this graph is bipartite. Okay. So what I'm going to do is the following. So take a vertex V, and I define left as the following. It's a set of vertices U such that the shortest UV path has an even length. And then V itself belongs to the left set, the set L, because the VV path has length 0, and 0 is even. And R is defined as a set of vertices U to which the shortest path from V has an odd length. And this gives you a valid partition of the vertex set. Right? I have a set L here, and I have a set R here. Okay. And let me take, so to show that this graph is bipartite, what you need to argue is that there's no edge between two vertices in R, nor two vertices in L. I want to argue that there's no edge between any two vertices from the same side. Okay. Well, that's because, but this is true for the following reason. Take U and W from R. Okay. Then what does that mean? There's an odd length path from V to U, right? Just because R is defined as the set of vertices to which there's an odd length path from this fixed vertex V, and that's the same as W. Okay. Let me add one more slide. So I have a vertex V, and I have a U here. This length is odd, and W has length odd. But if you have an edge between U and W, this has length 1, right? But then this is a close walk, right? You are completing this walk from V to U, and you move to W, and you go back to U. This is a close walk. what is the length of it? Well, what is the parity of its length? It's odd. So this is on odd closed walk. And we argue that, or I guess I said that this has to include an odd cycle. Any odd closed walk has to include an odd cycle. But we assume that, what we suppose that there's no odd cycle in this graph. So this is not possible. So we took two vertices from R, but the same argument holds for two vertices from L. Let's say I have L instead of R, and in this case, this will be even. This is even, but still the length of this walk will be odd, just because of this edge between U and W. Okay, so you also have an odd closed walk, and that will include an odd cycle. Okay. Yeah, question. Right. So it's a good point. So I'm assuming, so when you define this two sets, you need to assume that the graph is connected, or in the sense that there's a path between them. Well, when you have a graph like this, and you are taking V from this one part, then there's no path from this vertex V to a vertex from the second graph. That's just other point, but I guess let me not talk about this now, but we'll get to this later, okay? When we talk about connections. Okay. But let's assume that there's a path between any two vertices, meaning the graph is connected. But the argument is pretty much the same. Any other questions? Okay, so great. So let's get back to the statement. Again, a graph is bipartite if and only if it doesn't have an odd cycle. Okay. So then what you can do is, or what you can argue is that this graph, is it bipartite? Is it bipartite? It is bipartite because there's no odd cycle. Well, I got this question wrong when I was a student because it doesn't look like a bipartite graph, right? But what you do is, when you this is kind of like square paper. If you fold this paper, then this vertex will move on to this side, and your graph will look like this. Oh no, like this. And this is a bipartite graph, although it doesn't look like a bipartite graph. Okay. So again, if you don't have an odd cycle, it must be bipartite. It's an easy characterization. And you realize that odd cycles are what make the graph kind of difficult to analyze and stuff. If you don't have an odd cycle, you have a bipartite graph. Everything works really well for bipartite graphs. Algorithms are easy, but as soon as you have kind of complex structures based on odd cycles, and then algorithms have to be quite difficult or complex. Anyways, so because I have only 15 minutes, but I guess it's enough to talk about the bipartite matching problem. So we have a bipartite graph, and it's defined as the following. Again, the vertex set can be partitioned into two, like V1 and V2. And an edge has to cross this partition. One end has to be V1 and the other end has to be V2. You cannot take on edge two vertices from the same side and connect them. And if you look at this graph, I have this bipartite graph on the left. And the second one is also, okay, I need to define the matching. So what is a matching? So matching is, the formal definition is the following. So you are taking a collection of edges. so that if you take two distinct edges, they do not intersect. Okay, so if you look at this thing, if only one edge, so it's trivially a matching. You cannot take two distinct edges. But if you look at the second example, I have edge xw and gy. They are not they are intersecting in the sense that, I mean, so you are taking x and w and y and z. So these are two edges. They are disjoint. Okay. The definition becomes clear if you think about couples. I guess if I connect to a person with which I'm dating, I cannot date two people at the same time. In that sense, that matching edges cannot intersect. Okay. I guess we are not allowing double marriage, at least legally. You cannot marry to two different people. So you can then the definition of matching clear, right? Okay. So maximal matching is the following. So it's you are trying to make couples as many as possible, but somehow the graph doesn't allow to add more edges to your matching. If you, for example, if you look at this example, I have one edge in the matching, but as soon as you are adding one more edge to here, you are violating this matching structure because of this vertex. So you cannot add this blue one. You cannot add this edge YG either, because it will intersect with the red one. So this is already maximal in the sense that you cannot add one more edge to the current structure. Okay. Something that's related is called right. And maximum matching is a maximal matching, and at the same time the size is the largest possible. So this example on the right is also a maximal matching, and this is maximal matching, but this one is maximum, but this one is not, because the second matching has two edges, but the first example has one. So clearly, number two, the two edges is the maximum, where one is not. Okay, so this is maximal matching, but the converse is not true. Okay. Right. Great. So we have defined bipartite matching. So you are given a bipartite graph, and I have defined this notion of matchings. And we're going to focus on this concept of bipartite matching for the next 5 lectures. Okay, we're going to, I guess, go through every single algorithm that's known for solving or finding bipartite matching. So what is the maximum bipartite matching problem? So we are doing somehow optimization, and we are interested in maximizing the size of a matching, or we want to find the maximum matching from a bipartite graph. It's related to many applications in practice. Again, it's couple matching problem is a typical example, as the name suggests. Okay, and even in kind of more like realistic scenarios, I guess in the U.S. medical systems, medical students, when they graduate, they want to apply for some positions for their residency programs, and the government is running some matching system based on bipartite matching. Okay. Well, in fact, there's something more complex going on here. Like so each student has a preference ranking over hospitals, and hospitals also have some kind of prioritized areas when they hire. So you need to kind of take into account this ranking and preferences. That if you consider those rankings, then the problem becomes something called the stable matching problem, and we're gonna go through that in lecture 5 together. Anyways, and also the online advertisement slot selection problem is another example. Like if you look into Google, they have the ad slots. Of course, the top one or even the second top are the most preferred locations or spaces for advertisers. So you have to, the companies, if they want to upload their advertisement on Google, they need to beat or they need to compete with other companies as well. Okay. And the matching is allocated based on the bidding prices based on online auction. We'll also cover this in lecture 5 as well. Okay. There are many other applications like recommender systems, like Netflix has to recommend a set of movies to individual customers. You have a list of customers, and the other set consists of movies, and each customer has certain different preferences, and based on that, you want to match best things. And also matching markets. You have sellers and buyers. You need to assign one seller to a buyer, and so forth. And also job server scheduling. So let's say you have multi-processor systems, multiple jobs arrive at the same time. If you allocate multiple jobs to one server, then the server will just blows up and explodes. So you want to avoid that. Then you have to kind of allocate and arriving jobs to multiple servers kind of cleverly, and that's also based on part-time matching. We also have a professor from Korea Military Academy, and I guess in the military applications, I guess what we care about is the following. So we have a certain like missile defense systems. We have a set of weapons and missiles. When the enemy airplanes are coming up, we need to assign one missile to this one aircraft. And this is also an allocation problem based on bipartite matching. Okay. And there, the I guess important thing is that it's not that we have a whole entire set of enemy aircrafts. Maybe they are arriving in a random fashion and sequentially. Whenever one aircraft arrives, we are assigning one weapon to that arriving one, and we wait until the next one comes up, and we make the next decision later. And this has to be done in real time and in online fashion. So this is a variant of bipartite matching problem, which considers this kind of the online arriving objects. Okay. This is also covered in lecture 5. Okay. Any question? Okay, so we have 7 minutes. Let me talk about one algorithm at the end. Okay, we have, I think, enough time for this. We have enough time for this. So the question is, okay, we are interested in the maximum bipartite matching problem. Now the question is, how do we get one? Okay. And there's a natural algorithm. So what we do is the following. So we are greedily selecting edges. So we enumerate edges. We just number them, and then we just enumerate them one by one. Okay. But we cannot destroy this matching structure. We cannot assign one person to 2 different, people. Cannot. Okay. That's not possible. So as long as you are not violating or destroying this matching structure, you cannot add one edge to the matching structure. So we start from the empty set, and starting from the first set. So whenever adding on edge, remains the matching structure, keeps the matching structure, you can add it. If not, you cannot add it. Okay. So this is the simple greedy algorithm. What's interesting is the following. So of course, this doesn't give you a maximum matching, because here if you enumerate this H set as XY, XW, and YZ, and then because this is the first one, if you include XY, this is already maximal, and you can no longer add one more H to it, so you are done. And this doesn't give you on maximum matching because a maximum matching has to include XW instead of XY. That's unfortunate. But what we can prove is the following. At least, in the worst case, compared to the maximum size of a matching, this greedy algorithm can achieve 50%. So here's the exact statement. So if you have a bipartite graph, and I'm taking any maximal matching, okay? Again, a greedy algorithm has to give you a maximal matching, but I'm taking any maximal matching. It has to include at least half the number of edges in a maximum matching. This is what we can do. With the next 5 minutes, let me argue why this is true. Okay, so before going over the proof, and this is called something called an approximation algorithm. So in the worst case, I can guarantee a constant approximation of what an optimal solution can do. So whenever you come across this notion of approximation algorithm, it means that there's even though it's not an optimal algorithm, but it can guarantee at least something compared to the optimal solution. Right? Okay, let's go over the proof again together. So suppose not for a contradiction. Okay, so then there is a matching, another matching, M prime, such that the size of M is smaller than half of the size of this another matching M prime. And this gives you 2 times M and M prime. Okay. And let me enumerate edges in M. I have M. Okay. And I have 2 M vertices. So 2 M vertices covered by the edges in M. Okay. And in particular, M prime has more edges than 2M. Right? So what I do is the following. Maybe now I'm gonna look at the edges from M prime. It can be something like this or this. Okay, or even you can include an edge, the same edge from M. What you can argue is the following. An edge from M prime can okay. So okay, what you can argue is the following. Let me see. What I want to argue is that M prime has an edge UV such that U and V are not covered by M. This is what I'm going to prove 15 minutes later. Okay, let me stop here. and I'll give you the answer at the beginning of lecture 2. Okay. I'll see you again at 3:30.